An example problem. A simple Brayton cycle using air as the working fluid has a pressure ratio of 8. The minimum and maximum temperatures in this cycle are 310 and 1160 Kelvin. Assuming an isentropic efficiency of 75% for the compressor and 82% for the turbine, determine the air temperature at the turbine exit, the net work output, and the thermal efficiency, and use constant specific heats at room temperature. So we'll go ahead and then make that assumption 1, and of course that assumption will go along with it being an ideal gas. So to do this problem, let's first go ahead and we'll just go to the next slide and draw out our TS diagram. And I'll rewrite the assumptions here. So we have this problem, or this cycle occurs at steady flow. We're going to use cold air standard assumptions, which means ideal gas, constant specific heats, and we're going to assume no change in kinetic and potential energy of the fluid, of the air entering and leaving each process. And the pressure ratio is given to us, which is 8. So if I draw out the process, I get process for the idealized version from process 1 to 2 is isentropic compression. State 2 to state 3 is constant pressure heat addition. State 3 to state 4 is isentropic expansion, and state 4, that'll be state 4 isentropic. State 4 to state 1 is constant pressure heat rejection. Now this problem is telling us that there's isentropic efficiencies for both the compressor. So if you look at the compressor, you're actually going to have an actual outlet that occurs a little bit to the right of the isentropic outlet since there's entropy production. And same thing, state 3 down to state 4A, since there's an actual outlet of the turbine, which means that there's going to be some isentropic, or there's going to be some entropy production as well. Now I'll go ahead and write in that they give us the temperature at state 1, which is 310 Kelvin, and the temperature at state 3, which is 1160 Kelvin. So let's go ahead and find what the first part of the problem is asking for, which is the temperature at the turbine exit. Oh, and again, another assumption which I had forgotten to make is that we're going to assume the Q in and the Q out process is constant pressure, right? Because this is a non-idealized cycle. The non-idealized cycle, the way we look at it is that there's going to be a pressure loss in the heat in and heat out process, and also isentropic efficiency is less than 100% for the compressor and the turbine. But in this case, we're going to assume, since there's a pressure ratio of 8 and the problem statement didn't tell us anything different, we're just going to go ahead and assume constant pressure for both the heat in and the heat out process. So let's go ahead and try to find what the first part of the problem is asking for, which is the temperature of the air exiting the turbine, which would be state 4, the actual outlet temperature at state 4. So let's start at state 3. State 3, we have a temperature of 1160 Kelvin. Process 3 to 4 is an isentropic process for an ideal gas with constant specific heats. Well, let me just rephrase that. State 3 to in order to get the actual temperature coming out of the turbine, we're going to have to use the turbine efficiency, which is given to us as 82%. The turbine efficiency is described as the H3 minus H4 actual divided by H3 minus H4 isentropic. So that would be actual work over isentropic work. Now that we are using constant specific heats, we can factor out the Cp from the delta H to get Cp delta T. And we're also assuming cold air standard assumption, so the CPs are evaluated at the same temperature. So we get that the isentropic efficiency is going to be T3 minus T4 actual divided by T3 minus T4 isentropic. How do I get T4 isentropic? Well, that would be the temperature of an ideal gas with constant specific heats after an isentropic process. So T3 or T4 isentropic over T3 equals P4 over P3 to the K minus 1 over K. Now, just so happens that P4 over P3 is the inverse of the pressure ratio. So we can use that. We can find K in the ideal gas table, right? I think it's in table A2. And we can solve for T4 isentropic, which ends up being 640.4 Kelvin. And then using the isentropic efficiency equation, we can solve for T4 actual, which would be T3 minus the efficiency times T3 minus T4 isentropic. So we have T4 isentropic, we have T3, we have the efficiency, and we have T3. So we can solve for T4 actual to get the temperature of the air coming out of the turbine of 734 Kelvin. Now, let's go ahead and go to the next part of the problem. The next part of the problem is asking for the net work input, right? The net work input. The net work we can get by doing a first law around the whole cycle. We do a first law around the whole cycle to get the net work input. We're going to leave it in specific terms since we don't have a mass flow rate. It is Q in minus Q out. Now Q in happens to be H3 minus H2, and Q out is H4 minus H1. Now we can also further expand that since we are assuming constant specific heats. So I can factor out Cp from delta H to get Cp delta T. So this gives us the final form of the equation of net work is equal to Cp times, we can factor out the Cp totally because the Cp is evaluated at the same temperature, T3 minus T2 minus T4 plus T1. Now, in this, I have I'm given T3, I am given T1, and I have just, you see, I have T3, I have T4, and I'm given T1, so I have T4. The unknown is T2. So if I want to find T2, I know that at state 1, I'm given that the temperature is 310 Kelvin. Now I'm going to go ahead and find T2 much in the same way that I found T4 actual in the prior slide. So I'm going to go ahead and write out that I have an isentropic efficiency of my compressor of 0.75. That's going to be the isentropic work over the actual work. These are in specific terms, so that would be H2 isentropic minus H1 divided by H2 minus H1, which ends up being Cp T2 isentropic minus T1. Looks like, again, I can factor out the Cp from the delta H to get Cp delta T since I assumed cold air standard assumptions, which is constant specific heats at room temperature. So the specific heats cancel out. So in this, I have the efficiency. I have T1, trying to find T2 actual. So this would be H2 actual, T2 actual, but I don't have the temperature coming out of the compressor if the process was isentropic. So again, this would be an ideal gas coming out of a compressor with constant specific heat, assuming constant specific heat in an isentropic process. So I have to get the isentropic temperature coming out. So T2 over T1 equals P2 over P1 to the K minus 1 over K. P2 over P1 is the compression ratio. So I can use that to get T2 isentropic, 562 Kelvin. Now I take the compressor efficiency equation. I solve for T2, so that equals T1 plus T2 isentropic minus T1 divided by the efficiency. I plug in my numbers, I get 645.3 Kelvin. So now I have T2. So again, these will be the actual temperatures, right? T2 actual, T4 actual. So the actual temperature coming out of the compressor and the turbine. So knowing T3, knowing T2 actual, knowing T4 actual, knowing T1, I can go ahead and solve this and get a specific work out of 91.3 kilojoules per kilogram, or a work per mass coming out of 91.3 kilojoules per kilogram. So now I can finish off the problem. Part C, they're asking me to find the efficiency of the cycle, which again, the efficiency of any heat engine is 1 minus Q out over Q in, which equals 1 minus Q out would be H4 minus H1 divided by Q in, which is H3 minus H2. I can factor out Cp delta T, since I'm assuming constant specific heat evaluated at room temperature. That also allows me to cross out the CPs to get my efficiency completely in terms of temperature, and I can go ahead and solve this and get that the efficiency of this cycle is at 17.6%.